Students, the way to get started is to quit talking and begin doing. That is, dreaming is nothing without action. Take daily actions to turn your big dream into reality. No matter how small, every action you take gets you one step closer to your big dream. And every day you take action, you build a momentum.
Jai Hind students. So in today's lecture, we will discuss the combination of lenses when the two lenses are brought in contact with each other, or we will also discuss when they are separated by a small distance, then what will be the equivalent focal length or equivalent power of the combination. And thereafter students, we are going to discuss these very good and important conceptual questions, right? So let's first start with combination of lenses. So our topic is when two or more than two lenses are in contact with each other, like this. It may be either a convex lens or concave lens. So case 1, when they are in contact with each other, like this. Let us consider these are the two lenses, L1 and L2, and they are in contact with each other. These are the two lenses, L1 and L2. Their respective focal lengths are F1, F2, and their respective powers are P1 and P2. And they are in contact with each other, right? So this is the principal axis, right? So students, what to do is, suppose this is the object over here. Let us consider this to be a point object, and let us consider the distance be u. Now consider these are the reference lines from where the deviation of light is to be considered. So this is the incident ray. Obviously it will get refracted. Right? And if you consider the second lens to be absent, then the image will be formed somewhere over here. This is due to the first lens, L1. And any ray which is passing through the optical center will remain undeviated. This is suppose I1. And let us consider this to be V1. Right? So here I have not made use of lens L2. Only consider students lens L1 to be present. So this is the incident ray. It will get refracted, and in case the second lens were absent, then the image would have been formed over here, I1. So for lens L1, as per the lens equation, what you get is 1 by V1 minus 1 by u, this is the image distance and this is the object distance. It is equal to 1 by, what's the focal length of lens L1? It is f1. Put this as equation number 1. Right, students? Simply make use of lens equation. Now what to do is, consider lens 2 for lens L2. For lens L2, I1 will act as a virtual object. So I1 will act as an object. So now over here what happens is, the ray is coming. So it will get refracted from lens L2 as well. So it will be like this. So actual image will be formed over here. Let its distance be V. Right? So I is the actual image formed due to the refraction suffered by both the lenses. Right? So again I repeat, for lens L2, I1 will act as a virtual object, while I is the actual image formed. Right? And also students, remember, both the lenses are thin. So the distances from the optical center of either of the two lenses of the object or image formed can be considered to be same. Right? So for lens L2, what's the formula? Lens formula? 1 by V minus 1 by U equals to 1 by F. So 1 by V, image. For this lens, the image is this one. So its distance is V. Minus 1 by U. For lens L2, this one is the object. So U is V1. So it is 1 by V minus 1 by U is equal to 1 by F. What's the focal length of lens 2? It is F2. Clear, students? Again, I must stress on the fact that I1 will act as a virtual object for lens L2. So while making use of lens equation, U1 in magnitude should be equal to V1. And V, which is the distance of the image, that is equal to V only. And the lens L2 is having a focal length of F2. right? So what to do is, if we add these two, adding 1 and 2. So adding 1 and 2, we get 1 by V1 minus 1 by V1 get cancelled. So what do you get? 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. Put this as equation A. Right, students? Now, if we consider this to be a single lens, consider this to be a single lens. Let us consider this to be a single lens. This is a single lens. Of focal length say F, and let resultant power be P. So for this single lens, equivalent lens, the object distance is U, the image distance is V. So for equivalent lens, as per the lens equation, 1 by V minus 1 by U should be equal to 1 by F. F is the focal length of the equivalent lens, right? Put this as equation number B. So students, compare these two equations, we will get the result. So what do we get? From A and B, we get, from A and B, what we get is 1 by F is equal to 1 by F1 plus 1 by F. So this is a very, very important formula. So students, I must repeat the conclusion of this article. Whenever the two lenses, whether it is converging or diverging, or combination of converging and diverging, then the resultant focal length is given by this particular formula. 1 by F is equal to 1 by F1 plus 1 by F2. In case of n lenses connected in contact with each other, then the resultant focal length would be given by 1 by capital F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 plus 1 by F4 and so on. Right? So, we can represent the power of the equivalent lens as well. So, for that, what to do is reciprocal of focal length in meters, that will give us the power of the lens in diopter. So, in such a case, what we'll get is resultant power of the combination. It will be given by P1 plus P2. Reciprocal of the focal length, that's power. P1, P2 are the powers of the individual lenses. P is the power of the equivalent lens, right? And you're aware, focal length and power, it is positive for convex or converging lens. Focal length and power, then negative for diverging or concave lens, right? Also, the formula for the linear magnification, net linear magnification would be M1 multiplied by M2. M1, M2 are the linear magnification of the individual lenses under consideration. M is the linear magnification of the resultant one. So this is case 1. That is when the lenses are in contact with each other. Okay? This we have mathematically proved. And what about the second result? Now look. If the two lenses are not in contact, but there appears a small distance between them. Suppose these are the two lenses L1 and L2, its focal length is F1, its focal length is F2, and X with a small separation between these two. In this case, I will not prove it because it's beyond the scope of your curriculum, so I'll restrict myself to the formula only. So in this case, this is just from comparative point of view. So in this case, the resultant focal length is given by 1 by F is equal to 1 by F1 plus 1 by F2 minus X divided by F1, F2. This is the formula to be used when there exists a small separation between the optical centers of the two lenses under consideration. X is the small separation between their optical centers, right? This expression can be represented in terms of power of the lens as well. So the power of the equivalent lens would be given by P1 plus P2 minus X into P1, P2. So students, these are the formulas which we'll be using while solving numericals, right? This is the case where the lenses are in contact with each other. This is the formula which is to be used when there exists a small separation between the optical centers of the lenses under consideration. So, this is the theoretical portion. Now, let's practice some numericals, right? Let's start with the first question. Students, please read that question. First one. The first question is, two lenses of powers minus 1.5 diopter and plus 2.75 diopter are kept in contact. Find the resultant focal length of the combination. It's very simple, isn't it? What is the nature of this lens? Negative sign. It suggests that it is a concave lens or diverging lens. Positive power. It suggests that this lens must be convex or converging in nature. So they are kept in contact. This is the key point. They are kept in contact. So students, they are kept in contact. Means what's the formula for the power then? Just now we have discussed. P is equal to P1 plus P2. Since 1 by F is equal to 1 by F1 plus 1 by F2. Isn't it? So net power. It would be minus 1.5 plus P2 is 2.75. So it will be equal to 1.25 with positive sign. And this is the diopter. So the resultant power of the combination will be plus 1.25 diopter. So the equivalent lens will behave as a converging lens. Because the power of the equivalent lens is coming out to be positive. So it indicates the converging nature of the equivalent lens. Now we are supposed to find out the focal length of the combination. Focal length of the combination would be capital F is equal to 1 by P. P equals to 1 by F or F equals to 1 by P. So that is 1 over 1.25. This much meters. So it can be changed. So it is 100 divided by 125. So it is 4 by 5 meters or 0.8 meters or 80 centimeter. So I hope this is a very, very simple question and it's based on the direct formula of the combination of lenses when they are in contact with each other. Right, students? So that's question number 1. Question number 2. It's a good one. We have to make use of both the formulas, right? Let's concentrate on question number 2. Question number 2 states that there are two thin lenses. When in contact produce a combination of power 10 diopter, right? And when they are 0.25 meter apart, the power reduces to plus 6 diopter. So suppose the two lenses under considerations are having powers P1 and P2 and their focal lengths are F1 and F2. So when in contact, what's the formula? Resultant power is equal to P1 plus P2. So what is the resultant power when in contact? It is 10 diopter. That is P1 plus P2 is equal to 10. Put this as equation number 1. That's given. When they are 0.25 meter apart. When they are 0.25 meter apart. Then what's the formula for the power? It is P1 plus P2 minus X P1 P2. And then the resultant power is given to be 6 diopter. So it is 6 is equal to P1 plus P2 minus, what's the separation between the two lenses? That is 0.25. P1, P2. Right? So what to do is, let's substitute the value of P1 plus P2 as 10 over here. So we get minus 0.25 P1, P2 or 0.25 P1, P2 is equal to 4. Therefore, P1, P2 is equal to 16. 0.25 is 1 by 4. So on cross multiplication, P1, P2 will give us 16. Now look students. Now we need to proceed with the simple mathematical steps. We are having two variables P1 and P2 and two equations are there. We should be easily able to solve these two. Right? So what to do is, we can consider this. P1 minus P2 whole square, it can be written as P1 plus P2 whole square minus 4 P1 P2. We can write it like this. A minus B whole square is equal to A plus B whole square minus 4AB. On solving it, you will get the same as that of left hand side. So, let's substitute the value. So, P1 plus P2 is 10. 10 square would be 100. Minus 4. What is P1, P2? It's 16. So, it will be 100 minus 64. So, it is equal to 36. So, P1 minus P2 whole square is equal to 36. Which implies that P1 minus P2 is equal to 6. Put this as equation number 3. Right? Now, it's very simple. Consider 1 and 2. It can be easily solved. Add 1 and 3 and you should get the result. So, let's try. Simply on adding 1 and 3, what we get is adding 1 and 3. So, P1 plus P2 and over here P1 minus P2. P2 minus P2 get cancelled, we'll get 2P1. 10 plus 6, that is 16. So, P1 is equal to 8 diopter. Now, we are supposed to find out the focal length. So, power is reciprocal of focal length. So, implies that F1 it would be equal to 1 by 8 meters. That is 0.125 meters. That will be the answer. That will be the focal length of the first lens in SI, in meters, 0.125 meter. Now, if P1 is equal to 8 diopter, then P2 would be equal to 2 diopter. Substitute the value of P1 over here as 8. So, P2 will be 10 minus 8, that is 2 diopter. P2 will be 2 diopter, which implies that P2 is reciprocal of focal length of the second lens. So, which further implies that F2 equals to 1 by 2, that is 0.5 meter. So, these are the two focal lengths of the lenses, right? So, in this question, we have made use of both the formulas when the lenses are in contact with each other as well as when there exists a small separation between their optical centers. So, students, it was also based on direct formula. Okay, third one. It's not a numerical, it's a conceptual question. Concentrate on question number 3. Although the surfaces of a goggle lens are curved, it does not have any power. Now, even if the eye is perfectly correct, then also in order to provide smoothing effect, we make use of Ray-Ban glasses, goggles during summer, during extreme heat, isn't it? So that it gives us a soothing effect. So there is no sort of eye defect, but still we use that. And the surfaces are curved and still it possesses zero power. So we need to justify that. Now we know that whenever there is a transparent refracting surface having some curved surface, then it possesses some power. But here, although having curved surface, still its power is zero. That is to be explained. So let me first explain. These are the two lenses basically. This is the convex lens and this is the concave lens. This is the concave lens. This is the reference line. So what to do is, suppose we consider these two parts, this part and this part. If you combine these two parts, what will be the arrangement like? It will be like this. This part, right? This is suppose 1 and let us consider this to be 2. So this is the second part I have drawn and consider the first one. First one is like this. This is the first one, right? So combining these two, half portion will get this. So look, these two are parallel, these two are parallel, these two are parallel. One is concave, the other one is convex. Right? One is having positive power, the other one is having negative power. Both the surfaces are parallel. Students, both the surfaces are parallel. Although they are curved, but still they are parallel. Both the surfaces are parallel means that the radius of curvature are same. So as a result, the focal length of power are same. So power of lens 1, if it is plus P, then power of lens 2, which is concave, it should be of diverging nature, minus P. Therefore, they are in contact with each other. And whenever the lenses are in contact, we know that net power, it is given by P1 plus P2. So it will be plus P plus minus P. It would be equal to 0. So this is the proper mathematical justification of the fact that although the goggles are curved, yet it possesses zero power. So the reason is that the surfaces are perfectly parallel, isn't it? One is the convex, the other one is concave. So concave part will have negative power, convex part will have positive power, both in same magnitude. So since they are in contact, we must make use of this particular formula. So we get net power to be 0. Right? This is how the statement needs to get verified. So this was a very good conceptual question. Okay, let's try out question number 4. It's again a simple question based on theoretical explanation. 4. How do you explain the twinkling of stars? Students, do the stars really twinkle? No, not at all. It emits light continuously. Sun is also a star, right? It emits light continuously. Any star, it emits light continuously. So, why does the star appears to be twinkling? What's the reason for the twinkling of stars? Basically here, we are talking about those stars which are at a very, very far away distance compared to that of Sun. Sun is the nearest star to us, isn't it? So when we are looking at stars which are very, very far away, even very, very far as compared to the Sun, then what happens is, when the light from that Sun reaches Earth, then it has to cover certain distance through the Earth's atmosphere. So in vacuum, it's rarer. As it enters the atmosphere, the medium becomes more denser and denser and denser. So as a result, light from this star entering the Earth's surface undergoes continuous refraction. So as a student, what happens is, there is a shift in the position of the star. That is, the apparent position of the star is different from that of the actual position. So what I mean to say is that this is the surface, right? And this is the star. Suppose this is the star. Let us consider this to be the star. This is the original position, right? So this is the Earth's atmosphere. So ray is coming over here. So it will bend. On entering the Earth's atmosphere, it will slightly bend. So to an observer over here, it will appear as if the star is somewhere over here. This will be the apparent position of the star. So this is the actual position of the star and this is the apparent position of the star. And why there are two different positions of the star? Due to the atmospheric refraction of light. So this is understood, isn't it, students? There appears a change in the position of star due to the atmospheric refraction. Now the second point. Now the atmospheric conditions keeps on changing continuously with the time. With each second, the temperature, the density, it keeps on changing. The atmospheric conditions keeps changing continuously with time. So as a result, there is change in the refractive index of the medium, a slight change, but there does appear some change in the refractive index of the medium. So as a result, what happens is, this apparent position will also keep on fluctuating. So when the position of the star keeps on fluctuating, it gives us the twinkling effect. Understood? So again, I must repeat it. Stars actually do not twinkle. It emits light continuously. But when the light from the distant star enters the Earth's surface, it undergoes continuous refraction. And due to this atmospheric refraction of light, the apparent position of the star is different from the actual position of the star. And also, the second most important point is, the atmospheric conditions of the Earth keeps changing continuously. That is the density, the temperature, it keeps on changing continuously, resulting into the change in the refractive index of the medium. So as a result, this apparent position is also not fixed. It also keeps changing. It keeps fluctuating. So that gives rise to the twinkling effect of this star, right? So the main reason is, first, due to atmospheric refraction. Second, due to the continuous change in the atmospheric conditions. The apparent position of the star fluctuates, giving rise to its twinkling effect. So that is how you can explain the twinkling of stars. Okay, fifth one. Fifth fifth question is, for the same angle of incidence, the angles of refraction, three different media ABC are 15 degree, 25 degree, 45 degree respectively. In which medium velocity of light is minimum? So it's a very good question. For the same angle of incidence, I is given to be constant. Therefore, sin I is constant. Now, as per Snell's law, we are aware of it. As per Snell's law, we know that sin I divided by sin R is equal to refractive index, which in turn is equal to C by V. Isn't it? So, sin I by sin R is equal to C by V. Now, students, it's pretty clear. C is constant, I is constant, so sin I is also constant. C is the speed of the light in air or vacuum, which is 3 into 10 raised to 8 meter per second, which is constant. So, from this, what we get is C is constant, sin I is constant. From this, we can conclude that V is directly proportional to sin R. So, when the angular refraction is minimum, in that medium the velocity is also minimum. Now look, 15 degree is less than 25 degree is less than 45 degree. Therefore, sin 15 would be less than sin 25 is less than sin 45. Implies that velocity in medium A would be less than velocity in medium B would be less than velocity in medium C. So the light will have minimum velocity in medium A and it will have maximum velocity in medium C. So this question can be done using Snell's law, right? It states that the ratio of the sine of angle of incidence to the sine of angle of refraction is constant, which in turn is equal to ratio of C by V. Okay students, fifth question is also done. Now let's proceed with the last one, sixth question. Sixth question is a numerical, which is based on, I think, length equation, right? So let's do it. A length of focal length 12 centimeter. Focal length is given to be 12 centimeter. Produces a virtual image whose size is 1 by 3. Now student, key point. Size is 1 by 3. Means size of the image is less than the size of the object. And it produces a virtual image. So virtual and smaller size image is always and always produced by concave lens. So it must be a concave lens. And concave lens being diverging, its focal length is negative. So this is the key point. What kind of lens is it? So it is diverging. It is a diverging lens. That is, it is a concave lens. That we have found. By using the fact that in the case of concave lens, the nature of image is always virtual. It is always diminished in size. Here the size is given to be 1 by 3rd that of the object, right? So, focal length is given, size is 1 by 3. So it is erect, virtual and erect. So linear magnification is 1 by 3. Because H2 is given to be 1 by 3 of H1. Therefore, H2 by H1 is equal to 1 by 3. And H2 by H1 is the linear magnification. That is what I have written. And since it is erect, virtual and erect, so it is taken as positive sign. So, determine the position of the object and the image. So, let's do it. M is V by U. So, U would be equal to 3V. Therefore, let's make use of this equation. 1 by F is equal to 1 by V minus 1 by U. So 1 by minus 12 is equal to 1 by V minus 1 by, substitute the value of U as 3V. So let's keep on solving it. 3V. So here it will be 3 minus 1, that is 2 by 3V. Therefore, on cross multiplication, what do we get? 3V is equal to minus 24 or V equals to minus 8 centimeter. Right? So minus sign indicates that the nature of the image is virtual and erect. What about U then? U is equal to 3V. So it will be equal to 3 into minus 8, that is minus 24 centimeter. So by using lens equation and by using the concept of linear magnification, such numericals can be easily done. So students, please make use of the sign convention. That is absolutely mandatory. So So I hope students these questions are pretty clear. They're very interesting questions, and do practice as many numericals as you can, right? So, and one more thing, please ask your friends to watch the videos and also to subscribe, and definitely try to hit the like button. All the best then, students.